It's been a year, but I finally finished this video. I'm sorry it took so long, but few things pop up. One of which was over 1000 subscribers on my channel, to which I would like to thank everyone that contributed to this number. The added GPU theory at the later part of this video is my thank you for 1000 subs. I hope you guys like it. Now, I still plan to do videos when I find something interesting or when I decide that it's worth it. Don't expect a video every week or for a month even from me. But let's move on to the content of this video. I suggest jumping to whatever part you are interested in, as this is a long one. A short side note here. If you think I talked too slowly, just increase the video playback speed in the video options. Quick recap of what I did so far. I previously made 2 other videos about testing 22 cards, one of which shows them up close and another one showcasing performance of 8800 GTX card on my test platform. Here's a IDA 64 memory benchmark from said platform. In this video I will show results in graphs with my commentary on top. I decided to focus on DirectX 10 low-end options, or nuggets as we call them, and how they stack up to mid-range and high-end cards from DirectX 9C generation under Windows XP operating system. Alongside the graphs, there will be a video of 8800 GTX running said test. Here's a cheat graph of what I tested, which contains the basic specifications of cards like core makeup, vertex and pixel shaders, or shader processors, or CUDA cores in some cases, TMU and ROP number, bus width, GPU core or shader clock when applicable, and effective memory speed. Effective memory speed is twice higher than real clock, that will be shown in later charts, just so you know. All models tested were equipped with GDDR3 or DDR3 memory, except for X1300, which uses DDR2 type. They are run at the frequency selected by me, again, can be checked next to the card's name, which may or may not be what said card uses as stock. I did this for easier extrapolation of performance of cards from different vendors, one being overclocked while the others are not, or the same card having DDR2 memory instead of GDDR3 that I tested. Now onto the benchmarks. 3D Mark 2001 represents titles from DirectX 6 and 7 generation. It's mostly Fillrate and single-thread CPU performance bound, with some scaling with integrated memory controller. Has one test for DirectX 8 called Nature, but by itself it doesn't give a lot of performance points. There is over 3.5 times difference between slowest and fastest card in this test. At the bottom we can see Radeon X 1300 and 2 slowest DirectX 10 cards from NVIDIA, GT520 and GT210. The latter of which is faster by almost 15% from the former one, showing the GT520's weakness in either fill rate or lack of memory bandwidth. Next is 6600 GT and HD 4550, which score almost the same, and HD 6450 being almost 4% faster than Radeon X 1650 Pro. HD 3650 is dead even with 7600 GT's performance, which is overclocked by the way, and just 1.5% slower than Radeon X 1800 GTO. 9500 GT on the other hand is beating slightly overclocked 6800 GT by almost 3%. However, next card on the chart, Radeon X 1950 Pro, is over 7% faster. 3D Mark 2003 is a benchmark made for DirectX 8 and 9 class cards, but it does have DirectX 7 tests as well. Overall, it's not as CPU or platform limited as other benchmarks. I highly recommend testing older hardware with it if you can. There are many differences between results from this version and 3D Mark 2001 SE. 7900 GTX is still the fastest card, and X1300 is still the slowest one. Difference between them, however, increased to over 5 times. At the bottom of the chart with Radeon X 1300, we can still see GT 210, but instead of a GT 520, it's GeForce 6600 GT that is accompanying it. GT 520 is 7% faster than GT 210 in this test, showcasing Fermi's higher shader performance versus older Tesla architecture. Radeon HD 4550 is faster than X1650 Pro, but isn't quite at overclocked 7300 GT level. Should be on par with stock one though. HD 6450 managed to pass overclocked 7300 GT by a narrow 2.5% margin, and is faster than HD 4550 by almost 10%. On upper portion of the chart we can see clear performance jump between HD 3650 and X1950 Pro of over 24%. HD 3650 being a bit faster than X1800 GTO and X1950 Pro being slightly slower than 9500 GT. 9500 GT is 7% slower than 7900 GT and 4% slower than X1800 XT. 3D Mark 2006. I decided to separate Shader Model 2.0 and Shader Model 3.0 scores from overall benchmark score to avoid GPU performance from being biased by testing platform. CPU performance is taken into account when calculating 3D Mark 2006 overall score after all. Shader 2.0 scores show amazing performance of DirectX 10 GPUs in shader-heavy programs and games. 9500 GT tops the chart with 7% difference between it and the next card, the underclocked Radeon X 1900 XTX. HD 3650 and GT 520 are at halfway point between 7600 GT and X1800 XT, with X-series Radeon being just over 9% faster than mid-range DirectX 10 ATI card. GT 520 is over 20% faster than overclocked 7600 GT and represents the biggest performance jump between cards on this chart. HD 6450 and HD 4550 are both basically tied in performance with cards like X1800 GTO, X1650 XT, and overclocked 7600 GT. Even legendary Slowpoke, the GT 210, is faster than cards like X1650 Pro by 7% or Quadro FX 3400, otherwise known as 6800 GS, by 8%. In Shader Model 3.0 test, 9500 GT drops to second place, with X1900 XTX being 11% faster. Regardless, it is still 8% faster than other underclocked GeForce 7900 GTX and Radeon HD 3650, both of which have basically equal performance in this test. HD 6450, GT 520 and HD 4550 place in the middle of the chart, with GT 520 being faster than 4550 by 4.5% and HD 6450 being faster than GT 520 by 5%. Slowest of the three, 4550, is 7.5% faster than X1650 XT. GT210 is again the slowest DirectX 10 card, but is almost on par with overclocked 6800 GT and 4% faster than X1650 Pro. This is the last synthetic benchmark I will show before game results. If you are interested in similar tests, please skip to later part of the video. Quake III Arena. This is the first game test. I'm using the later 1.32 GOG version of the game, and as such I'm not using the usual demo 001. I'm also using trilinear filtering as texture filter, along with highest texture detail quality set on the bar above it. Cards placement is similar to 3D Mark 2001 SE, but there are exceptions. HD 4550 is being just a bit slower than X1650 Pro by 2%, and HD 6450 being slower than HD 4550 by 5%. The most notable difference is 4 DirectX 10 cards at the bottom places and ATI reigning supreme on top 3 spots on the chart. However, this is a bit irrelevant as all cards have over 230 FPS average result here. Because of this, I omitted this game from average performance chart. Crysis results show similarities to Shader Model 2.0 scores from 3D Mark 2006, like chalk topping 9500 GT and underclocked X1900 XTX being the runner-up when sorted by average FPS. This may be natural as this game heavily relies on SM 2.0 code. However, that's where similarities end, as real-world performance is influenced by more than just pure compute capabilities of cards. Doing average frame rate is a bit dull though, so since the chart already shows that, I will change things up and base my commentary on card places based on minimum frame rate. Now, it's underclocked X1900 XTX that is the new king of the hill, with HD 3650 and X1950 Pro being tied as runner-ups. First Nvidia cards, 9500 GT and underclocked 7900 GTX, both tied like previous ATI F.E.A.R, are slower by around 12%, making ATI cards sweep the top 3 spots, just like in Quake III Arena benchmark. Jumping back to average FPS for a bit, the above 30 FPS score of HD 6450 makes this card the slowest one you can reasonably play in this game at those settings and resolution. This card also matches the minimum frame rate of 7900 GT with mere 18 FPS. I could end comparison here, since next cards aren't exactly playable, but there is always decreasing resolution or details to get back playable experience. Next we have HD 4550 and X1650 XT F.E.A.R, which shows similar average FPS. However, DirectX 10 card will suffer a bit more based on minimum FPS. GT520's 16 FPS minimum frame rate makes it twice as fast as X1800 GTO and 20% faster on average. GT210 is just struggling here though. Based on average score, GT210 is 6% faster than overclocked 7600 GT, while having 1/3 of its minimum FPS. Doom 3 is OpenGL game that likes old Nvidia cards, as can be seen with underclocked 7900 GTX and 7900 GT being top. 9500 GT is tied with X1800 XT, which itself isn't that much slower than X1900 XTX. HD 3650 is 9% faster than overclocked 6800 GT and 4% slower than overclocked 7600 GT. Next, low-end Nugget, or HD 6450, is tied with Quadro FX 3400 and is a bit faster than 6600 GT, while HD 3550 is 7% faster than GT520 and 27% faster than GT210. The last Nvidia DirectX 10 card is on par with X1650 Pro, the second slowest card on the chart in this game. However, both can still deliver over 60 FPS average performance. Far Cry is CryEngine 1 game and is the predecessor to Crysis. Let's start from the bottom cards with GT210 that is showing its superior shader performance with average FPS of 23, making it 6% faster than X1650 Pro. At the same time, however, an overclocked 7300 GT is 10% faster than the slowest DirectX 10 card. GT520 is doing quite well with 29 FPS average, which positions it pretty close to an overclocked 6800 GT. HD 4550 is tied with overclocked 7600 GT and X1650 XT in performance, with HD 6450 being 7% faster than all of them. Top performing cards are a big jump away from HD 6450 score though, with 9500 GT reaching 56 FPS average, a midpoint between X1900 XTX and 7900 GT, making it 10% faster than HD 3650, which itself is 5% faster than X1950 Pro. Next game, F.E.A.R. Back in the day, a killer one for both GPUs and players alike. It's relatively shader heavy, but can be easily limited by rasterization performance in GPUs. Slowest modern low-end nugget, the GT210, shows good performance with average score tied with Quadro FX 3400 or 6800 GS in this case, but at the same time has higher minimum FPS of 21 versus mere 15 FPS of NV41 based card. HD 4550 and HD 6450 are on par with stock clocked 6800 GT, with HD 4550 being around 9% faster than 6450. This provides some insight into how much shader power is needed to make F.E.A.R playable at those settings. GT 520 outperforms X1800 GTO by slight 2% average margin, but is 8% faster based on minimums. On the other hand, top cards like HD 3650 get 60 FPS on average, and it gets pretty close to X1800 XT with 63 FPS average, still matching its minimum frame rate. Top cards are separated by noticeable performance jump from slower ones. 9500 GT is almost as fast as X1950 Pro on average and beats it in minimums by solid 10%. This was the last game I tested. Next up is geometric mean of all games and summary and conclusion. Game average is, as mentioned, calculated based on geometric mean of average FPS across 4 games and does not include Quake III results. We can clearly see the 3 performance groups created here. Slowest one, with performance of around 30 FPS and lower, contains cards like GT210, 7300 GT, Quadro FX 3400, 6600 GT, X1650 Pro, and X1300. Second group is slower mid-tier with close to or a bit over 40 FPS average scores. Slowest card in this group is 6800 GT with GT 520, HD 4550 and HD 6450 representing DirectX 10 and 11 era entry points. X1800 GTO, X1650 XT and 7600 GT from NVIDIA are other classic DirectX 9C models also present here. Lastly, we have high-end with over 60 FPS average score. X1800 XT opens this group with 2 DirectX 10 mid-range offerings, the GT 3650 and 9500 GT. High-end DirectX 9C cards like X1950 Pro, 7900 GT, 7900 GTX and X1900 XTX are all faster than them. Based on those results, I recommend avoiding cards from low performance group, which is under and around 30 FPS average, as they may not provide the necessary performance you may need to run DirectX 9C games at quality levels that I tested here. You can lower the visual quality settings, of course, if budget or availability are limiting you, but let this be warning to those that want to play retro games from this test at maximum quality settings. Those cards aren't for you. When classic DirectX 9C high-end cards like X1900 series or 7900 series from NVIDIA are keep getting harder and harder to come by, low mid-tier DirectX 10 models like HD 3650 and 9500 GT, with 8600 GTS being also in there, are a good alternatives. If you can't get them, lower mid-tier performance ones should still be there to save you. The ones with 40 FPS average score in my tests. However, always check memory type of your card before buying it. DDR2 versions of some cards I tested here do exist and can be up to 30 to even 40% slower than the cards I tested here. Again, check frequencies of your cards you are buying with the values I provided on each chart near the card's name. Thank you for watching this far. If you are only interested in game performance, I suggest moving on to the next video. But if you are interested in nitty-gritty parts of the tested GPUs, I have some bonus charts for you. Before we move on, here's a quick rundown of what's ahead. There will be a block diagram in the bottom left corner showing how things flow inside GPU. Parts of it will be highlighted in red depending on what each test was meant to check. My idea was to show each part of the GPU and what it does to data it processes, or how we get pixels on screen from basic data points in space using a GPU, which will be visualized by a triangle in the bottom next to the block diagram. Sadly, I had to compromise on software since there is simply no ideal programs capable of showing what I wanted to show. Please don't crucify me in comments from obvious shortcuts I took here. First chart isn't as information-packed, but later on I recommend pausing the video if you need more time to take it all in, as they say. Memory bandwidth. It's where we start at primary external metric that determines GPU performance, and what can limit it a lot if not done right. Why that is? As you can see on the highlighted parts of the block diagram in the bottom left, in short, it's simply needed everywhere. Usually, how much bandwidth a graphics card gets is based on a viable technology like GDDR3 and PCB manufacturing, and is adjusted to segment of the market it was made for. Multiplying bus width and effective memory speed gives us gigabytes per second metric you see in this chart. It helps that those cards are all within 5 to 6 years of each other, as changing memory technology can make this a lot more complicated. I hope this explains performance of entry-level DirectX 10 cards in earlier part of this video. Of course, bandwidth by itself doesn't guarantee performance at all. It only enables fast GPUs to show what they can do. Newer architectures are made to take as much as possible from what they get. That's why newer mid-range DirectX 10 cards like 9500 GT and HD 3650 can compete with high-end models from years earlier, despite having only 2/3 of their overall bandwidth. Moving on. After data gets sent through PCI, PCIe or AGP bus to its VRAM, GPU starts crunching it. First stage in this process is Vertex Shader, which manipulates corners of triangles, the vertices, to reach desired effects. In case of 3D Mark, we have two tests. Both can be seen in the bottom right corner. In a simple one with the grass, and a complex one with 4 high-quality monster models appearing at the same time. Camera movement and model movement are used to increase the difficulty of this test. This is a synthetic test, which shows how good each architecture is at manipulating different amounts of Vertex Shader data. DirectX 10 cards have unified shaders, which helps them increase their efficiency by large margin in similar tests. Rasteriser. Basically, a stage where we change from triangles in 3D space into pixels in 2D space. This test should rely heavily on Vertex Shader to overload Rasteriser part of the GPU by flooding it with big number of triangles to process at the same time. This is one of the compromises I had to make though, since there is no such ideal test to be downloaded anywhere. In Codecreatures benchmark, for example, developers used alpha textures to show nice and pretty landscapes at the same time as many triangles are pushed through the GPU. This can limit overall performance by running into fill rate limitations on lower-end cards, even before Rasteriser gets actually stressed. This is a limitation that real-world performance can also run into. Classic synthetic versus real-world collision here. Based on original idea of pure Rasteriser test, however, there are no cards that should be limited by Rasteriser performance in this lineup. Only later cards with multiple Rasterisers, like GTX 780 or other GK110 based cards, can run into issues here. Like overall performance of Rasterisers, limiting maximum pixel fill rate performance. Still, even then it's more to do with how many pixels can all Rasterisers push out at the same time, versus how many triangles can be processed. There is no point in making pixels unless we know what color they are. Textures are usually 2D representation of wallpapers that GPU uses to wrap 3D objects in, with the idea being it needs to start somewhere. Texture operations are one of the most bandwidth-intensive tasks a GPU can do, other than color blending in the last stage. There are many types of textures, and in the real world there is usually the need to use multiple textures on the same object even, hence the name multi-texturing. This test shows multi-texture efficiency of each GPU. Cards lacking bandwidth or not optimized for using textures used by this test will have bigger gaps between measured and maximum performance. This is pure synthetic test. After texturing, GPUs can manipulate pixels containing texture data however they like through pixel shader units. There are many different effects that can be used here. Just check how many tests a shader mark benchmark can perform. Regardless, if you are still interested how cards should perform if fill rates aren't the issue, I suggest going back to introduction part of this video and cheat sheet chart that I made with each card being ranked by number of pixel shader units and some CEO math on top. However, that's not how real world works, and as such I'm using Codecreatures results here. This test measures performance of layering 4 textures on an object. Its performance penalty is massive versus what cards can do in theory. Of course, some GPUs are better than others at it, which can be seen on ATI's DirectX 10 low-end ones catching up to overclocked 6800 GT or X1800 GTO. The last stage to finalize pixel color is called color blending and is done on ROP units of GPUs. Because there are multiple ways you can blend colors, or even how colors are represented mathematically, I choose to use 2 tests here, which are also used by actual games. First one is alpha blending, which is used to make objects that can be seen through. Alpha blending was used extensively in Codecreatures benchmark, which prevented it from testing pure Rasteriser performance. It's also one of the most expensive single operations of its kind a GPU's ROP does. Having enough bandwidth to feed data into ROPs is crucial. Second chart is color plus Z fill rate, or calculating color of pixels alongside discarding those that are behind others. Main reason for this is as 3D sync gets flattened to 2D, some objects will be obscured by others, and you don't want to calculate color of pixels you won't be able to see on the final image. Here's where the Z part comes in, as it contains the value of how far each pixel is from the viewer, making it relatively easy to figure out which pixels will be seen and which will not. Color data from ROPs is saved into frame buffer, which is used by RAMDAX to display final image on the monitor. Congratulations for sticking with me so far. I hope my results from last part can become the base for other videos that will dive more deeply into architectures of those GPUs. Maybe explain why they perform like they do? I didn't do it in this video as I personally don't see myself as qualified to comment on the reasons behind their performance. I wish you all good day or night, depending on when you watch this.